The first topic in the module 1 is basic operational concepts. Here you have to know if the instruction is to add two numbers or two registers, you will have this opcode and you will have this operands. The processor is having 5 parts. These are for storing the register these are for storing the instructions. This will store the data and this will have the control signals, and the instructions will be performed in ALU. Then there are few steps to perform each instruction, which is first will PC is the program counter. This will give the instruction to MAR means memory address register. This will have the address of the instruction, and MDR will have the actual instruction that will be sent to IR instruction register. This will have all the instructions in that, and that will send to ALU for performance of the instruction, and the result will be stored in a register RN. Now single bus structure, you can consider this as a road, means if you have some input from here that is stored to be stored in the memory, that will travel from this path till the memory. That's same for all of this. Now if you have multiple bus that's known as multi-bus structure. Okay, suppose that there is a task A and which is to be performed, and this task can be divided into 5 parts in 5 clock cycles. Clock cycle is nothing but a particular amount of time, like 0.1 seconds. Now task A takes 0.5 seconds to get completed, so it will have 5 clock cycles, and total time taken can be calculated 5 into each clock cycle, which is 0.5 seconds. Basic performance equation is this: T is equal to ns by r. Now what are these things? T is the time required to execute the whole instruction, means the whole program, and n is the number of instructions, s is the number of cycles for each instruction, and r is equal to 1 by p. P is the time for one cycle. Now if r is equal to 1 by p, I can write 1 by p here, so I will get the equation as nsp. Now in nsp what you will have, suppose this is the whole program, it will have 5 lines of code, and each line takes 10 cycles to execute. So and one cycle which is p is taking 0.1 seconds. Okay, each cycle is 0.1 seconds, and there are 5 instructions, so the total time will be calculated as 5 instructions into instructions, how many cycles are there for each instruction, and time taken for each cycle. So if you multiply that, the total time can calculate for the whole program, which is 5 seconds. All the information which we have in the computer is stored in the form of zeros and ones. Suppose that this is a memory and it will be divided into many blocks, and each block will be divided into zeros and ones, and these are all known as the cells or the bits, and a group of 8 cells is known as a byte. Okay, and there are 2 ways of assigning the addresses. Suppose I need to store any number. Okay, for storing every number 8 bits are required. So for example 78's binary equivalent is this, and I'll store it in 8 decimal places, 8 binary places. Now each of this, see, this whole can be compressed into this small part, like that, different number here, different number here, different number here. So if you store 4 of these like this, that's known as one word. Okay, and this will be stored in one particular block of the memory. This will have the address 0, this block has the address 0, this will have 4. Why 4, 8 like that? Why? Because 0 is here, this will be 0, 1, 2, 3, then again here it will have 4, 5, 6, 7, 8, 9. Understood? Like that. Now we have 2 ways, which is big endian and little endian. Now in big endian what you will have, the memory will be starting from here, just as the previous one, 0, 1, 2, 3, 4, 5, 6, 7. Now suppose I had to store these numbers, and before that let's see what is little endian. In this you will have the address starting from right side, 0, 1, 2, 3, 4, 5, 6, 7. Okay, just opposite of this. Okay, now suppose I have to store these numbers. Okay, 12, 34, 56 and 78 by both methods. Now for this method, how I'll store, I'll start 12 storing here. Okay, I'll store the 12 here, then 34, then 56, then 78. But in little endian what I'll store 12 here, 34, 56, 78. See, if you read from the memory, it will be in reverse order. The memory reading will start from here, but the storing will store from here only. Okay, so the address will be 0 for this one, 1, 2, 3, but in big endian it will be like this way. Okay, till now we have seen how the data is stored in the memory, but also but instructions are also stored in the memory. Let's see how that is happening. See, these are the blocks for storing the instructions, and in these blocks you will have the instructions. Suppose I have to add 2 numbers a and b and store the result in c. I have to add 2 numbers and store the result in c. For that 3 lines will be required. Move a to r0. A A will have the number, R0 is a register to store any information. Register is nothing but it will store some data. So I'll move A to R0. Now in next instruction I'll add B to R0, means what R0 has that will get added with B and it will be present in R0. Then finally I will move R0 to C. In these two instructions I added A and B, then that sum will be transferred to the C. Okay, that are the 3 lines for instruction execution. So these are the address and these are the contents for the instructions to be executed. Suppose that there were many numbers I had to add, like 1 2 3, like that I had many numbers. Okay, now for that instead of writing again and again add n1, add n2, add n3, what I can do, I can just write once, add a new number and then repeat the same process again and again. That is known as branching. How I will do? First see, move n to R1. N is the total number of digits. Okay, suppose I had 4 digits, so n is 4, I will move R1 to 4 and clear R0. R0 is having nothing, R0 should have nothing, it should be empty. Then next the program starts from here. Add new number to the R0, means this is the first number 1 will be added here. Okay, so I'll have 1 here. Next decrement R1, this is 4, this will become 3 now. Now branch is greater than 0 is nothing but R1, it should be greater than 0. If it turns out to be 0, means all the numbers will have added till then. So loop, if branch is greater than 0, it is greater than 0, loop means again go back here, add new number to R0. New number is 2, so add 1 plus 2 which is 3. So like that for all numbers it will happen and this will get 2 1 0. When it comes to 0, what will happen, it will have the sum which is 10 and move R0 to sum, means you have to move this sum into the variable named as sum. Okay, that's the final answer. Our task is to find out if the result of this particular thing is negative or not. I'll take two registers or variables A and B. A will have 4, B will have 6. If A minus B is less than 0, means 4 minus 6 will be calculated, that's minus 2. If it is less than 0, condition flag should become 1. So this will become 1 here. After that becomes 1, what's the thing? Print result is negative if it is 1 here. That will be checked, and if it is 1, it will print as negative, or if it is 0, like previous it was 0, right? If it is 0, print that result is positive. Okay. So according to this, if it is negative, then only the condition will become 1 and this will be printed, or else it will be positive only. There are 5 different types of ways in which you can address the instructions. First one is immediate addressing. What does this mean? The instruction will be of this type: move hash 200 comma R1, means whatever will be with hash, that will be moved into R1, means R1 will have 200 now. Next one is direct addressing. This is the memory. In memory you will have some digit here and it will have some address. Okay, move LOC comma R1, that will move the data which is present in this particular location to R1. R1 will have 21. Indirect addressing means you will have 3 registers here. Add square brackets R1 comma R0. What will happen? See, observe here carefully. Square brackets of R1 means R1 has some value. Okay, this value is what? This value is the address of another register, and this register has the operand. I need 45. Okay, so this 45 is stored in R2 whose address is stored in R1. Okay, when you use this instruction, it will be executed in this form. So add R1 square brackets R1 to R0, which will add this 45 to R0 here. Okay. Next one is register addressing, which means move R1 comma R2, what value R1 has, that will be moved to R2. Next is index addressing. In index addressing it will be of this form: add 20 in brackets R1 comma R2. Now R1 has 1000, R1 is stored at 1000. Suppose this is R1 is stored at 1000 and 20 R1. What does 20 R1 mean? 20 R1 means 20 plus R1, which is 1020. So add the contents after 20 locations from R1, means R1 is at 1000, after 20 locations it's 1020, which will have the operand here. That operand should be added to R2. Next we have auto increment and decrement mode. Suppose I had to print these numbers in the form 12, 41, 32 in the output. How will I do? Usually how will I do? I'll print R0, then I will say print R1, then R2. Instead of that, I can just use this equation. In this by using this instruction, what I will do, R0 will be printed, then it will be incremented to R1, then it will be incremented to R2. So this will be printed. If I have to print in the if I have to print in the reverse order, I'll use decrement. Okay, so it will be printed in this form. We have our own language and computer has its own language, but computer doesn't understand our language. For that we need to translate our language to computer language. Between our language and computer language there is a language which is known as assembly language. This will be similar to the computer as well as to our language. Let's see how it is. See, we'll use the words like move, add and increment, right? In the assembly language it will be of this type. Okay, so it's translated using the assembler. For example, sum is equal to 200, we will write like this, right? But in assembler language it will be sum EQU 200. Okay, this is the assembly word. Next topic is basic input output operations. This is the bus which will transfer the information from one part to another part. These are the three units, which is processor, data in, data out. This is the input. Suppose this is connected to keyboard and I input any letter, that will go here and it will go to the processor in this form. And data out means from the processor some data will come and it will be outputted through data out. And S in and S out are nothing but these are the conditions which, if I start to click any key in the keyboard, this S in will turn 1, which will indicate that the processor that and data is coming, so it has to store the data. Similarly for S out also. Next is stacks and queues. Stacks is nothing but a part of the memory which is divided into many blocks and each block has some address here. And SP is the stack pointer. Suppose I have some data in one of the blocks and SP will point to the latest data added. Okay, so SP is 12 now, it's pointing to minus 28. Suppose I had to add another data which is 14. What I will do first, I will move this to empty place, means 8. It is at 12 now. If I have to move into 8, so I will subtract 4 initially. Subtract 4 comma SP, then SP will be moved to 8, then see move 14 comma SP, so then 14 will be moved to this location. That's known as push operation. Another operation on the stacks is pop. Pop means deleting an element. Actually the element will not be deleted, but it will not be considered by moving this SP to the next location. So the stack will be considered from this position only. By adding 4 you will get the SP from here to here. So the stack will be this will not be considered. It's as same as deletion of the element. Queues are also same as stack, but it will have 2 pointers, which is rear pointer and front pointer. You can insert an element from this and delete an element from this. That's the only difference between stack and queue. Suppose that I had to add two numbers a and b and print its sum many times in the program. So instead of writing this program like add a, b, print sum many times, what I can do, I can collect this at a different place and I can give some name like sub and I can call whenever I need it. Okay, so if I am executing the instruction, whenever I need to call, I can use this call sub. So I need not repeat it again and again, and I can just call it once. So that's known as subroutine. Instruction will be going on, and at that time when I will call this, it will go to the different place and it will get executed, and after the execution it will return to the normal execution of this main program. Let's talk about stack frame. It has many parts. Let's see one by one. These are the instructions in the memory. Okay, and this is the main function. Means suppose the instructions are getting executed from here, and these are the variables in this main memory. Okay, and this main memory has I1, I2, call average, means this is another subroutine which is getting called here. So when I'll call this, it will go to another part of the program and finish this and then again execute what was getting executed. So how the things will happen. What is stack frame? Stack frame is nothing but whenever I call a subroutine, the variables I was using in the main, that and the variables which the call average has, that will be stored in this stack. Stack is nothing but area where you can store the variables. Now see, when I call this function, what will happen? This stack will be created, an area in the memory will be created, and it will have three parts: local variable, arguments passed, and return address. So what's the thing here? What are local variables? Local variables are the variables present in the main function, which is I1, I2, I3 and I4. This will be stored here, I1, I2, I3 and I4, and then call average. So if I call average, if it has some variables, that will be stored in arguments passed. And the return address is nothing but after this gets executed, from where I should start the main instruction 1 to 46, right? So that will be stored in return address. Let's see it by an example. See, start from here. This is the main. the same as the previous one. So when I call this call average function, what will happen? Call average is defined as this. This is average function, and in this function the variables are p1, p2, p4. Okay, forget about this, just focus on this here. This is the main function and this is the called function, which is average. Now what will happen when I call this, when I execute this instruction, an area will be allocated in the memory, which is this area. Okay, what does this area have? This area will have the local variables i1, i2, i3 and i4, which is from the main. This will be stored in the local variable part, and in arguments passed, what will be stored? p1 and p2 and p4, p1, p2 and p4. These are the variables passed from the called function, which is p1, p2, p4, and then the return address will be stored 1242. See, the return address is this. After this gets executed over, it should start execution from 1242, right? So it will be stored in the return address in this stack frame. Now suppose that when I called this function and it was getting executed, it had another call to the another function. So what will happen now? When this call is made, another function is another stack is needed to store the information of this call, right? So that will be stored above this stack. Okay, above this stack this will be stored. In this also same will be there, local variable, argument passed and return address. Now this is the called function. Okay, and this is the main function. Now in this main function the local variables are p1, p2 and p4. Okay, so in this stack the local variables are p1, p2 and p4, and the arguments passed are q1 and q2. Okay, so this is q1, q2 will be stored, and after this gets executed, means call division gets over, it should start the execution from 1266, right? So that will be stored in the return address here 1266. Okay, so when this gets over, this will be executed, and when this gets over at 1242, the execution will begin again from here. Okay, so that's the stack frame operation. Now one more topic is stack pointer and frame pointer. See, suppose these are the three stacks. This is first stack, second stack and third stack. Local variable, arguments passed, return address, like that three are there. Now stack pointer will always point to the top of the stack. Okay, but I need to access the arguments passed and the return address. So for that accession I will use frame pointer. That can move between these both, but stack pointer will always point to this. So when this stack's part is over, what will happen? This stack pointer will point to this local variable top, arguments passed and the return address will be accessed by frame pointer. That's the difference between frame pointer and stack pointer. Here we have two concepts, shift and rotate instructions. Let's see one by one. Shift instruction. In shift instruction, what you will have, suppose that before you had these numbers, this is in the register and this in the carry. Now what does shift do? If I insert a 0 from here, means I insert a 0 from here, this all will be shifted by left by one side. So this 1 will come here, this 0 will come here, this 1, and so on. And the last 1 was here, so when I inserted 0 here, this 0 will come and stay here. That is known as logical left shift, because I am shifting the bits by left. Similarly, the right shift is like this, and then comes the rotate operations. In rotate operations, you will have two parts, rotate left without carry and rotate left with carry. Let's see how it is. It's same as the shift instruction, but in this will not insert any number manually, it will get automatically inserted. Let's see how it is. Suppose you had these numbers here initially, and when you will rotate left without carry, what will happen? See, when you will rotate, this will come here, 1 will come here, 0 will come here as usual. Okay, but then this 1 will also come here. See, 2 1s were there, now 3 1s are here. In rotate left with carry, what will happen? Before these were the numbers, now with rotate left with carry, this will be considered. So 0 will come and sit here. See, 1 1 was there, now 0 is also here, and this 1 will be going here normally, and this all the numbers will be changed normally. Just the 0 which is carry, that will be considered and it will come and sit here. Okay, that's rotate left with carry. Similarly, you have rotate right also, just the direction will be opposite. This is the last topic of module 1. In this module, there are some instructions, which means the instructions how it will be stored in the memory. See, add r1 comma r2, this is the one word instruction. So add will be stored in the part of the memory as opcode, r1 and r2 will be stored as source and operand, and some additional information such as control signal, condition flags, or condition codes or branching statements. Other information will be stored here. This is the organization of the instruction which is stored in the memory. Second type is two word instruction. In two word, you will have this immediate I mean indirect register addressing. You remember in indirect register addressing you will have this R1 which is in the square brackets. What does that mean? This has the address of the operand, not the operand itself. So you will have to execute the instruction in 2 steps. So for that you will have move operation in the opcode. Source will have this R1 and R2 will be in the destination, and the immediate operand which is in between R1 and R2, the actual operand address will be stored here and the other information will be stored here. And if I had to add 3 operations, 3 numbers which are R1, R2 and R3, what I will do? First I will add R1 to R2, then I will add R2 to R3. So for that we need opcode R1, R2, R3 and other information such as condition codes and all will be stored in this fashion. Module 2 has to do a lot with input and output. So let's revise what is single bus structure. See, this is the bus and it is connected with the computer part which is the processor and the memory, and these are the devices connected like keyboard, mouse and printer and all. So this is the bus and the data transfer takes place between the IO devices and the processor as well as in the memory. Now IO interface, what does an interface mean? Interface means this is the computer part and this is the input device part like keyboard and mouse. What does an interface do? In interface, see, when you input something in the input device, that will go and transfer to the bus. Before that it has to know the address where that key has to be sent, and the data which is A, what data has to be sent, and the control lines, how and when it should be sent, that is decided by these 3 things. It will get separated into 3 lines, and this is just one bus but it has 3 lines inside it. Okay, so this is the interface which does this whole part. The first way is pretty simple one, program control IO. In this you will have this desktop here and the input here which is the keyboard. This is the output, this is the input. Whenever it's going to show any output, this output signal will be activated so that the processor will know that output has to be shown. Similarly, for whenever I enter some key, this input signal will be activated so the processor knows that input is getting in, it has to give the signal to take in the input. So the processor checks again and again if this signals are either of these signals are activated. According to that it will control the whole functioning of the computer. Second one is interrupt IO. In interrupt IO, suppose that the computer execution is normally going on, and between that at any time if I give some input, so it has to stop its normal execution and focus upon what I have given the input. This normal execution of the computer will stop here and it will take in the input and do all those things. That is known as an interrupt. Okay, so here is the processor and these are all the devices connected, and this is the line through which the data gets transferred from the devices to the processor. Data will be sent by the devices to the processor. Okay, so whichever device needs to send data, this switch will be closed and the data transfer is possible. Other all switches will not be allowed to send any more data until this data gets over. Since many devices are connected to the same computer, it's pretty obvious that there might be chances of multiple devices giving the data at the same time. So how to handle those multiple devices? There are few techniques. First one is polling. In polling, what will happen? The processor will be checking again and again which device has requested for an interrupt. Interrupt means it has to send some data in the bus line. So processor will be checking and which data will be interrupting first, that will be given the priority to send this data over the process line. This device has to wait until this device transfers whole data to the line. Vector interrupts is another way of handling these multiple devices. See, in this the processor will be connected to many devices through a line which is the bus, and each device will have one ID with it. Okay, so whenever any device makes an interrupt request, so that ID will be sent to the processor and the processor will identify which device has sent that, and that device will be given the permission to transfer the data on the bus line. Okay, another one is interrupt nesting. This is a bit different. In this you will have many devices connected to the processor in a particular order. Okay, this is the processor and each device is connected in this fashion. So first device has most priority and the priority goes on decreasing in this form. Suppose that this device is getting the instruction executed, so, and in between the first device interrupts the processor to get instruction executed, so the device of 2 will be stopped, this instruction will be stopped and this will be started, and until this finishes this can't resume its instruction. Okay, so that's known as interrupt nesting. A way to implement interrupt nesting is daisy chain. This is the daisy chain method. The processor is connected to many devices and this is int r, means interrupt request line. And see, what happens is, suppose the device 2 has interrupted an request and it has sent the request in the interrupt request line to the processor, and the processor will send int a, means int interrupt acknowledge. means it will send to the device 1. So first device 1 will be checked. If it has no request pending, it will transfer this int a to the device 2. Otherwise its instruction will get executed first and then its instruction will be executed. So the priority goes on decreasing in this fashion. This is known as daisy chain method. In direct memory access, you will have the memory and the device connected directly, and the processor having some control over the memory and the device, but much less as compared to the other techniques. Okay, in direct memory access, it's a very fast access, and it's used only for some transfers which are very urgent and important. These three registers combine to form the DMA controller. This DMA controller controls the transfer of data from the device to the memory. Bus arbitration. Arbitration means selection. See, this is the bus and many devices are connected to it. Suppose two devices interrupt at the same time, means they have to transfer the data. Which device will be given the priority? See, that's selected by the processor. In the first case, centralized arbitration. In centralized arbitration, the processor will send BG. BG means bus grant. These are all the devices connected, and BBSY means bus busy, and BR means bus request. So whenever any device has to make a request, it will send that request in the BR line. BR line will be sent to the processor. Processor will check if the bus is not busy here, bus busy is not, it's free, then it will send a BG to the first device. If it doesn't have any request to pending, then it will be sending to until that requested device reaches and that device gets its instruction executed. Suppose that there are two devices with the device IDs 5 and 6, which is 0101 and 0110. These two have requested to transfer their data on the bus. So which one will be selected? Let's see how it works. 0 will be stored here, 0 1 0 1, and this 0110 will be stored in this form, 0110. Now what will happen? These two will get OR, logical OR. What is logical OR of 0 and 0? It's 0, right? So 0 will be here. Then logical OR of 1 and 1, it's 1. This also 1, this also 1. So this ID will be taken, and what it will be doing, it will be compared with this ID. So write this ID below this ID, 0 1 1 1, below these two IDs. After writing, then you have to compare the digits. How you will compare the digits? If it is same, write the same. Okay, 1 and 1 1. If there is any difference, write 0, and the subsequent digits will also be written 0. Wherever the mismatch happens, write that digit as 0, and the further digits will also be made 0 without any further comparison. Similarly for this also, it will be 0 1 1, mismatch occurred, it's 0. Okay, so then these two are the new IDs of these both devices that will again be sent to this parts here. Okay, means 0 1 1 0 will be placed in this lines as 0 1 1 0. Okay, these are the new ID, and this 0 1 1 0 is the same ID, so it will be same. Now what will happen? This is 0 1 0 0, sorry, this is 0 1 0 0. Okay, this is the new ID of 5, new ID of 6. Both are placed. Next step, what you need to do, again do the logical OR. 0 and 0 logical OR is 0, and this 1 and 1 logical OR is 1 1 0. This is the new ID, logical OR ID. Now again you have to compare which ID is matching with this. Is this matching? No. Is 0 1 1 0 is matching with this, right? So 6 wins the arbitration, and 6 has the permission to place its data on the bus. Okay, moving on to some further depth about the buses. See, bus will be shown as this, right, but it will have 3 lines separately, which is for data, address and control line. It's obvious from the names what are these functions, and those functions will be performed for this all devices. Okay, now there are two types of bus transfers, which is synchronous and asynchronous. Synchronous means there are, the time is divided into sections of many. If some suppose that a task is there, task A, it requires a particular amount of time, like 5 seconds. Okay, so each time can be divided into 1 second breaks, so that all seconds will be known as bus cycles. Okay, those all time gaps will be known as bus cycle. See, each called as one bus cycle. One data transfer can take place in one bus cycle. So the task, whole task will be divided into few parts, and in each part, a part of the task will be executed. Suppose, take an example here. Processor wants some information from a memory location. See, this is the processor. Okay, and this is the memory. Okay, see here, this is the memory, and one data is here, and the processor wants that data. See, the data is here and the processor wants the data. So what it will do, it will be executed in 3 steps. In the first cycle means in the first time gap, what will happen, master places the places a command to read the data. Master is who? The processor. Processor will place a command to read the data. That will only happen in the first cycle. In the second cycle, slave places the data on the bus, means after the first cycle, in second cycle slave will place the data on the bus, and in the third cycle master will read the data and put in the input buffer. That's what happens in the synchronous bus transfer. The time will be divided into the slots, and in each slot a part of the command will be executed. It will be happening in the 4 steps. See, the same thing, master wants some data from a memory. Okay, now what happens, master gives a signal to read the data. Okay, master gives a signal. Now when the slave acknowledges that signal, then it gathers the data and gives a signal to the master that it is ready. When it gives the master the signal, the master will read the data on the bus line. Okay, so that's what happens. So it's very fast than synchronous, because the faster they send the messages and execute the information, the faster the transfer will get over. Okay, you need not wait for the time slots. Every device has 2 parts, one is user part and one is computer part, which has processor, and the user part is controlled and the user controls the mouse, keyboard and a touch screen. Okay, between these both, this is IC is interface circuits. You might have seen in your laptops where you plug in the charger port and all, that port is known as the interface circuits. It connects the interior part of the computer with the outer part of the computer. Okay, that port you have to clearly know what it is. That port is very important. In that there are 2 types, the parallel port and the serial port. Let's see what a parallel port is. See, this is the keyboard. Okay, suppose I typed a letter A. Okay, that A has some ASCII value. That ASCII value will be encoded by this one. That encoded value, suppose it is 0101. Okay, it is encoded in binary and it is sent to the IC. IC is the port. Okay, IC is the port, and inside that port it will be sent, and that will be sent to the processor through data line, control line and address line also. Okay, you have to focus a lot on this. In IC, what's the input coming? Input is coming from the keyboard, right? That's the input. What's the output? Output has data line, control line and address lines. Okay, remember, now we will go into the further depth regarding this particular IC. Okay, let's see how it works. Now it's time for you to recall what I had told you. See, this is the IC, this whole thing. Okay, this is the IC and this is the input coming from the keyboard. Okay, and this is the output, data line and control signals and the address lines. Okay, in that image, remember, IC was here and the keyboard was input from here, and the output was to the processor, data line, address line and control line, right? These are the data line and this is the control line and this is the address line, and this is the interior part of IC and this is the keyboard data. Okay, so let's see what's the working of it. Start from here. Whenever a data comes in the keyboard, this valid will become high. Okay, when valid becomes high, status flag will become high. This data will be stored in the data in only. Then come to here, read write. The processor will issue the read write signal, and this will be high, means it needs to read or write, and master is ready, that will also be high now. So these are the address decoder. What does this address decoder do? It will select which device has to be performing the function now, means the keyboard is performing the function, right? So that address of the keyboard will be decoded by this one, and this will also become high here. So see, observe here, where are the numbers high here? Read write is high, master ready is high, and this address decoder is high. Now last left is A0. See, A0 is connected to a NOT gate here. Okay, so if A0 also needs to become high, what it should be? 0, right? It should be 0, right? When it is 0, then this NOT gate, it will pass through the NOT gate and it will become high here. So that's the same thing happening. This will pass through the NOT gate and this will become high here. Okay, so these all are high, means this AND gate will work. Okay, after knowing that, what does this AND gate do? This will read the status. See, when this is connected to a OR gate here, this OR gate will become 1, means see, since this AND gate became high here, this will be 1 and this 1 will be sent to the OR gate. Now this OR gate will have 1 here, so this will be executed and slave ready will be shown. When slave ready signal is shown, what does that mean? That some data is here, that the processor will know. So when this data is here, what it needs to do? It needs to read the data. For reading the data, A0 will become 1 now. Why A0 will become 1? Because A0 is connected to read data also here. So when A0 will become 1, these are all already 1. So when A0 also became 1 here, this will read the data. Read the data means this is connected directly to the this part, right? And what does this have? This has all the data which I have inserted. It has traveled to here. So this will become readable and all this data transferred to the processor. This is the data line and it is connected to the processor here. Okay, This is how the 8-bit input parallel port works for keyboard. Same is for printer also. Just the printer will have the output here, the data will come from here, and the same things happen here also. And coming to the next one, which is combined. Okay, see, the data in and data out both had the same things, address, decoder, everything was same. So if we combine, it will look like this, and the function is all same. In serial port, you will have all this data coming in serially, bit by bit. Okay, first 1, then 0, then 1, like that. Okay, so it will be coming in serially, and once 8 bits are inserted in this, it will all shift parallelly, means at the same time all will transfer to data in. This data in register will go to this one. What is this? These are the data lines connected to the processor. Okay, so all this data will be gone to the processor. Similarly, if it is for output, all the data will come from the processor and the output will happen parallelly here. See, the data out will come parallelly, but it will get outputted to the screen bit by bit, 1 0 1, like that. Okay, that's the working of serial interface. Now what is standard IO interface? It means this is the processor, this is the keyboard, both are connected by a wire here, and here is the port. So there should be some basic standards, right? Means which should be same for every device, so that every device will accept so that every device will be connectable to the processor. So let's see what are those. So suppose that these are the processor and the memory, those are connected to by the processor bus. Okay, so that the data transfer will happen between the processor and the memory here. Okay, and then all the devices, these are the input devices like keyboard, computer, keyboard, mouse, printer, and all, everything will be connected to the processor bus, so that their data will also be transferred into the processor bus. Okay, but by doing so, the processor bus will become very busy and it won't work properly. So what's the solution? The solution is include another device here which will control which device should only one device is allowed to do at a particular time, and that data will be transferred here and that will be gone to here. By using this, you can control the transfer of information in a more efficient way. What is this device called? This is called PCI. Okay, PCI, and this bus is known as PCI bus. Okay, a peripheral component interconnect, it's the full form of PCI. By using this bus, you can control the information transfer. Now see how it looks. It looks like this. These are the devices connected. Okay, these are devices connected to the PCI bus, and this bus is connected to the main memory, so that it helps in the controlling. PCI bridge will control which device should put the data in the main memory at a particular time. Okay, SCSI bus is the same as PCI bus. It will have the same bus here and the controller here, and all the devices will be connected. But one feature of SCSI bus is different. That is, see, SCSI controller, it gives the request to SCSI bus that it needs this data. So what will happen? That SCSI bus will give the command to this controller to collect the data. So while collecting the data, it takes some time, right? So within that time, this bus is free. Another unit can use this bus, right? So that is a special feature, which is overlap of data. Means at the same time, two can be used. While this is collecting the data, this bus can be used by another device. Okay, that's the specialty of SCSI bus. Rest all things are same as PCI bus. Now the last thing is USB. USB we are all familiar with. If you have to connect multiple devices, what you will do, you will use this device, have this connection with the laptop socket, and this will be having many more sockets here. So in that form, you can connect multiple IO devices as well as many other this type of USBs. Okay, that by using USB, you can connect multiple devices through a single port. All the information in the USB is in the form of packets. Packets are of two types, data packet and control packet. Data packet has the information, and the control packet has the address of the device or the acknowledgement or the control signals and everything. Now each device is made up of different fields. This is the PID. PID will be common to all the data fields, whether it is a data packet or a control packet. Okay, what does this PID do? PID helps in identification if it is a control packet or a data packet. Okay, in case of control packet, what will be the case? PID will be there and the address and other instructions will be there. In data packet, PID will be there, along with it data will be there. In module 3, you have to know what are the processor and the memory and lines which connect both of these. These are the address, data and control line. Now what are these uses? Suppose the processor wants to read some data from the memory, what it will do, it will send in the control line a command that it needs to read the data, and the memory fetches that data and puts in the data line, and the processor reads this data. Okay, now if the processor has to write some data in the memory, what it will do, it will send an command that it has to write the data, and it will send the address where it has to write, and what data it has to write will be sent in the data line, and the memory will take all of these inputs and write that data in the particular address where it has to be written. Okay, those are the two functions of processor and the memory: read data and write data. Next comes the cache and the virtual memory. See, cache is present in between the processor and the RAM. RAM is random access memory, which will be discussed in the more detail in the upcoming video. Now see, the RAM and the secondary storage has one thing which is virtual memory. Now let's discuss what is cache first. Cache will increase the speed. How it will increase? Some data will be accessed between the RAM and the processor, it will pass through the cache. Now the most recent or the most used data will be present in the cache, so that processor whenever it needs, it can just take from the cache and it need not search in the RAM. If it is present in the cache, it is known as a hit. If it is not present in the cache, it is known as a miss. In case the miss happens, processor has to take the data from the RAM. Coming to virtual memory, it is present between the RAM and the secondary storage. What happens is, whenever RAM needs some data, if it is present in the virtual memory, it will take from it, otherwise it should have it will fetch from secondary storage. The address given by RAM is virtual address, and the physical address is the actual address which is stored in the secondary storage. Okay, what does this virtual memory do? It will store some information which is most accessed by the RAM, and if it needs some more information, then that previous information will be overwritten by the new information which is needed. Okay, that is known as virtual memory. Talking about semiconductor RAM memories. In semiconductor RAM memories, you will have, first start from here, I'll go through each of this part sequentially. You will have 16 rows here, numbered from W0 to W15. So this row, all the rows will have the address as this numbers binary equivalent. Like this row will have the address 0000, this will have 0001, like that 15th row, 16th row will be having 1111. So these are all the addresses, and each row is having address. So the row which I have to select, I will put in the binary values here 0000, then this row will be selected. Remember, you are using 4 values of binary for having 16 rows. That means 4 digits of binary means there will be 16 rows. 2 raised to 4 is 16, right? So if you use 4 the inputs, you will have 2 raised to 4, which is 16 rows. Okay, now after having rows here, you will come to the columns. See columns, how many you have from B7 to B0, 16 rows and 8 columns. Now R and W, focus on this part here. R/W means read or write. Whether I input read or write, that operation will be happen on these cells. Okay, suppose I inserted R, read. Okay, read means sense. Okay, W means write, read means sense. If I inserted R, the reading operation will be happening on these cells. Okay, which cell I have to make the reading happen, that will be selected by the row here. That row will be selected and this column will be selected, and in that particular column and the row, that thing will happen either read or write. Okay, now these are the rows. I'll insert the data from here, from B7 to B1 to B0, all the data will go in and the data will be selected, and the read or write operation will be happening on each of these cells. Suppose I selected the first row, which is by inserting 0 0 0 0, then this row will be selected and the read or write operation will be happening on all of these 8 cells. This whole thing is known as a chip. Okay, and the CS, I will come to that later, which is known as chip select. This whole thing is one chip. Okay, this whole, including the address decoder and the sense write circuit, everything along with these cells is known as a chip. The next topic is organization of 1K memory chip. 1K means 2 raised to 10, that is 1024. Okay, 1024. Now if I have to store 1024 memory cells, like see, one cell is nothing but it's a box which can have either 0 or 1 value. Okay, that is known as a cell. Like that, if I have to store 1024 cells, okay, like that 1024 cells, if I store it in a single row, it will be very long thing, right? So how is the organization made in the computer? Let's see how it is made. See, instead of storing 1024 cells consecutively in one row, what I can do is I can use 32 rows here. Okay, 32 rows here and 32 columns. Now if I use this 32 rows and 32 columns, the total number will be 32 into 32, which is 1024, right? 1024 cells will be stored in this fashion. Okay, that will take much more smaller space than if I put it in a single row. Now for distributing the number of rows, see 32 rows means how much? I had told you initially, you need to remember, if there are 32 rows, that means you would have 5 address bits, means 5 bits will indicate the address lines. See, address lines are this rows, this is the rows, okay, from W0 to W31 means 32 rows are there. For indicating each row, I'll have the binary equivalent 0 0 0 0 0 5 times, okay, because for indicating the 31 the binary equivalent is 5 ones, right? So I need 5 binary values. If I have 5 binary values, I'll take in 5 bit row address, means 5 bits will be sent like 0 0 0 0 0 for this first row, or any other binary equivalent for the particular row, okay, that is for 5 bit row. Now 5 bit row will give me 32 address lines for the rows, and I should have 32 address line for the column as well, right? So the remaining 32 row columns will be sent by 5 bit address columns, okay. So this 5 will be gone here, and 32 columns will be made here, and 32 rows will be made here, okay. So this whole memory chip will be here. Now there will be total 10 bit address lines divided into 5 bit row and 5 bit column, okay. And this is the read write signal, which you already know. This is sense write circuitry, and this is the chip select, means this is one chip and this will be selected, okay. This is the organization of 1K into one memory chip. If in externals they ask, you have to explain it in this fashion. And this is the data input and output, which row I select and which column I select, in that particular what data I have to put, that I will be inserting in this. There are two types of RAM, which is static RAM and dynamic RAM. Let's see one by one. In static RAM, you will have two inverters here, okay. What does this inverter do? It will store the data, or it will write the data, or it will fetch the data, okay. Now see, these are the two transistors used here, okay. Now what does these transistors do? See here, when these transistors are on, you can either read or write the data that will be given from the word line. If there is some data in this, okay, if there is some data that will be sent through the word line, through the transistors it will go through the word line, or if there is some data which is to be written, that will be coming through the word line, through this transistors it will be written. Now how to specify if we have to write or read the value? See, it's very simple. If you have to read the value, this B will be high and B dash will be low, or if you have to write the value, this will be low and this will be high. Just as these inverters are used here, instead of that, in CMOS cell what will be the case? These transistors will be used to simulate the working of inverter. These two will act as upper inverter and these two will act as lower inverter, okay. That's the only difference between CMOS cell and the static RAM. Asynchronous DRAMs will be a bit cheaper because they will not have any transistor in them, but they will have capacitor. Now what does the capacitor do? See, these are the capacitor. It will store the charges. For the charge on the capacitor will be getting over again and again, so it has to be refreshed frequently within every few milliseconds. Now in every memory cell, either of 1 or 0 has to be stored. So in this memory cell, either 1 or 0 has to be stored. Now what will be the case? If the bit line is high here, then it's 1 will be stored and the word line will read it. How the word line will read? If the transistor is on, the data will be transferred. Now if there is no charge in this, that means a 0 will be stored and the word line will read it when the transistor gets on. This is a very important question with respect to exams. Now see, 2m into 8. What does 2m into 8 mean? First of all, let's see that. What is m? M means 2 raised to 20. Okay, 2 raised to 20 is known as m. Okay, now we have to store 2 into 2 raised to 20 into 8. 8 is the inputs, okay, so just forget it. 8 are the inputs, so we have to store this much value inside this cell. Okay, now how we will do that? Now we'll have this divided into rows and columns. How many rows will be there, how many columns will be there? 4096 rows will be there and 512 columns will be there. Rows and 2 raised to 9 columns. Okay, that means 4096 rows and 512 columns. That will be distributed accordingly. And what is RAS and CAS? That means it is the address and column latch. Now when the address and column are, when the row and column are ready, this RAS and CAS will give the command to decode it. Okay, so this will be decoded and sense write and sense read will do the work accordingly if it is for reading or writing operation. and the memory will be stored here. That's the internal organization of 2M into 8 dynamic memory chip. You need to remember 2M is for this one. 2M is divided into rows and columns, and 8 are the inputs going inside. Okay, D0 to D7 are the inputs, which are 8 inputs. Fast page mode. What is a fast page mode? These are the rows and these are the columns. Okay, so if I have to read some value, like see here, as you can see, I have written a word here, apple. Okay, I have to read all these letters. Now first what I need to do, I need to select this row and select this respective columns and read each one by one. Okay, so for that I will select a row and then select this column and I will read it, and then again I will select a row, then again I will select that column and I will read it. That's a very long process. So in fast page mode, what we do is, it's a shortcut. We will select the row once and save that row address in this latch. Okay, this latch will have this row address, so I'll just need to change the column for reading all these letters. Okay, so that's the fast page mode. Next is synchronous DRAM. In synchronous DRAM, it's all the same thing. You will just have a refresh counter, and the data retrieval and the writing will be controlled by some clocks which is inside the processor. Okay, so for example, see here, in this you will have these data read. Okay, D0, D1, D2, D3. Okay, these are all the data read at particular signals. Okay, see, whenever you need to read or write data, you will output this. If you have to read, you will read write signal will turn on, and that read signal will turn on, and this data output register will be having the output here, and this read write circuit latches will turn on. Now this refresh counter will refresh all these values, and this data will be read one by one at each cycle. Okay, 4 data if they have to read, like data of length 4, each will be read at one cycle. That is synchronous DRAM. Now here the question is to store 2M memory with 32 input data lines. Now what does this mean? This is a structure of larger memories. Let's see, remember this 2M memory with 32 input data lines. Okay, now I have to store 2M memory cells. Now how much is 2M? 2M means 2 raised to 2 into 2 raised to 20. Okay, 2 into 2 raised to 20 is 2 raised to 21. Okay, 2 raised to 21 memory cells are needed to store. Now dividing into 4 parts, how much I will get? If I divide 2 raised to 21 by 4, how much I will get? That is 2 raised to 19. Okay, now for each of this will be 2 raised to 19 rows. Okay, so total number of rows will be this much, 2 raised to 21. If I divide, each row will be 2 raised to 19. Okay, 2 raised to 19 rows. 2 raised to 19 can be written as 2 raised to 9 into 2 raised to 10. Okay, that can be written as 2 raised to 9 into k, because 2 raised to 10 is k, right? So 2 raised to 9 is 512k. So each of this chip, this is known as a chip, that chip will have 2 raised to 9, which is 512k rows. Okay, 512k, 2 raised to 9 into 2 raised to 10, that is 512k rows, and 8 inputs. Okay, it will have 8 inputs, because I need to store total 32. Remember in that question, I need to store 32 input lines, so it will be divided into 4 parts, 8, 8, 8, 8. So inside each of these 8 inputs will go. Okay, now you remember what was a chip in the previously I discussed. Inside a chip there will be an address decoder, and there will be many rows here, and this column will be here. It will have sense, read, write circuit, right? Now in this case there will be 19, because it is 512k, right? 512k is 2 raised to 19, so 19 address lines should be required. 19 bits should be required to specify this all 512k rows. Okay, so 19 address bit lines will go here, and this column lines, what how many column lines? 8 column lines. So this will be 512k into 8 memory chip. Okay, 512k into 8 memory chip. Like that, if you use 4 of these, this will be 2m. That will be 2m, because 512k into 4 is 2m, and that's what we needed. This will be 2m memory chip. Okay, means 2m words will be there, but we needed 32 inputs. For this 2m, it's just 8 inputs are there, so like that 4 times we will use for 32 inputs, and that's the structure of larger memories. Okay, next thing is memory controller. What does a memory controller do? In memory controller, you will have between the processor and the memory, you will have memory controller that will divide the number of rows and number of columns. See, in that previous video you had had told you, right? The processor will be here and the memory will be here. Now some rows will go here and some columns will go here. Like 5 rows and 5 columns for 2 raised to 10, right? So that division will be done by this memory controller. Next is Rambus memory. Rambus memory is a faster type of memory, and the speciality of it is, see, whenever you, this is high and this is low, okay, this means 1, this means 0. Now whenever you differentiate between high and low, it will be going in this fashion. That will be very slow. But what does a Rambus memory do? It will reduce this length, which will reduce the effective time and show the differences faster, okay. So that is the speciality of Rambus memory. The differences will be shown faster, so the data transfer will be done very fast rate. Moving on to the ROM cell, which is read only memory cell. It is a secondary storage device, okay. In that, see, this is one cell, okay. In this cell, either 1 can be stored or 0 can be stored. Now if I have to store 1, what I have to do, I'll have to remove this connection. If I remove this connection, it will not be connected to ground and it will be high, okay. So that 1 will be stored. Now if I have to store 0, I just have to make this connection so that it will be connected to ground and this will store a 0. That's the basic cell of a ROM. There are 3 types of ROMs. Programmable ROM. In programmable ROM, you will have this, it can't be edited. See, whatever you write the code here, it can't be edited. That is programmable ROM. But in next, you have EPROM. In EPROM, if any code is written, it can be erased by UV light and you can write it again. And EEPROM is nothing but electrically erasable programmable ROM. In that, you will erase that by using electricity. By using the electricity, the code can be erased and rewritten again here, okay. That's the EEPROM. Now considering the speed, size and cost of the units, it is in this fashion. See, this is the processor. It has a faster memory and it can retrieve the data very fast, so its speed is increased, and while the speed increases, the cost is also increased, okay. Now coming to the below part, in below part you will have the main memory and the secondary memory. The size will be increased. You can store larger memory, but then it will decrease the speed as well as the cost will be very low, okay. This will be very cheap comparison with the faster memories. Cache memory is a memory between the processor and the main memory. What it does is, the most frequently accessed data will be present in the cache, so the processor can get the data directly from the cache and it need not search for the main memory again and again. That will save a lot of time for the processor. But on the other hand, if there is no data on the cache which is which the processor needs, then in that case cache will find the data from the main memory, and that effect is known as miss, okay. If there is no data in the cache which the processor needs, that is known as miss. If there is a data, that is known as hit, okay. And each of these has a formula and numericals associated with it. Since there are a lot of transfers between the main memory and the cache, there are 3 types of mapping, which is known as, first one is known as direct mapping. In direct mapping, what will happen, see here, this is the main memory, okay. These are all divided into the many blocks, okay. The main memory is divided into many blocks here, and these blocks are mapped into this cache, okay. Now how does this work? See here, this is the processor, and this processor requested a memory like block 1 memory, block 0 memory, and that will be brought to the cache first in block 0, and that will be gone to the processor. Similarly, block 1 will go here, and block 2 will go in the block 2, like that till block 27 I can take. If the requested data is from block 128, where it will be stored, it will be overwritten in block 0, again repeating. Then block 129, if I access, it will be stored in block 1, it will be overwritten, like that it happens, okay. That's the mapping of this main memory into the cache. This type of mapping is known as direct mapping. The next type of mapping is associative mapping. Let's see what is in this. See, in this it's the same thing. The main memory is divided into many blocks, and these blocks are mapped into the cache, okay. So this is the cache, and the main memory is mapped into the cache. Now see what happens, block 0 will point to block 0. Now if any other random block will come, it will point to the block 1, like that. Any random block will point to the block 2, like that. In order it will be stored. It does not have a specific order. What will happen if all the blocks are filled? In that case, what will happen, the least used block will be overwritten. That's known as replacement algorithm, okay. The least used block, which is the most oldest block which was not used frequently, that will be overwritten with the new block which is required now. The next one is set-associative mapping. In this, what will happen, it's the mixture of direct mapping and the associative mapping. by this, see, there will be many sets made. Okay, the sets will have two blocks in it. Okay, in the inside the cache. Now what will happen, each block will be mapped to one set. Okay, like block 1 will be mapped set 1, block 2 will be mapped to set 2, block 63 will be mapped to set 63. Now see, when it goes inside a block, and if it finds that two blocks are there, but one of the block is filled and another block is empty, then it's okay, it will go and it will be filled in that block. But if both the blocks are filled, what will happen, it will check which block was most oldest. Okay, means the oldest block will be replaced and overwritten with the new block. That's set associative mapping. In that, many sets will be made, and that's the only difference between this and the previous associative mapping. In order to know which is good in performance, how we will do that, see, consider here, this is the processor and the memory. Okay, now the performance depends on two conditions: how fast the memory will send the data required to the processor, and how fast the processor will execute it. Okay, there are some ways to enhance it. First one is interleaving. In interleaving, what we will do in normal method, see, in normal method the address will be here and these are the data modules. Okay, here data will be stored. If I want to fetch some data, it will search in this module first, then if it didn't get, it will search in this module. Like that, it will take more time. In interleaving method, what will happen, it will search all at the same time parallelly, and which in which block the data is available, that data will be sent on this line, and the address will know that the data has found, and it will stop the searching of other modules. So interleaving helps save a lot of time. Second is write buffer. In write buffer, what you will have, suppose the processor needs to write some data onto the main memory, so that what it can do, instead of waiting for the cache to fetch the address and all, what it can do, it can give the write buffer. This is the write buffer. In this unit, it can give the unit the task to write the data, and it can carry on with the other processes. So simultaneously it can do the other process, and this write buffer will handle the writing of the data into the main memory. That will save a lot of time. The second way is prefetch. Prefetch means even if it gets some initial signals that it might need some data, it will give that information that it needs, maybe it will need some data in the near future, so that memory will make arrangements for that data. That is known as prefetch. The last one is lockup free cache. This is another method which is used to make the process more faster. Suppose there is a transaction going on between processor and the cache. Okay, and the cache doesn't have some data. Okay, so it needs to fetch from the memory. Till that time, what will happen, processor can't use the cache because cache is busy in getting the data. So in order to make it more efficient, what can happen, you can use a special register here which will handle the fetching of the data from the memory. At the same time, processor can use the cache simultaneously, while other register will be handling the fetching of the data from the memory. This will save a lot of time and it's more efficient.